Hey guys, in this video we're going to talk about titration curves. Now this is really important because they like to ask some questions dealing with this, as well as you are also required to be able to sketch titration curves, and it will also later on help you be able to see the big picture after we learn all the individual components. So what I have written out here first is things that you will have to know how to do. So this is a scenario in which you will be given a titration curve and you have to kind of pick it apart, decipher some things from it. So the very first thing is determine which components are involved. And so what that means, now that you have an understanding of what your titrant is and what your analyte is, you have to understand, be able to look at the titration curve and figure out what your titrant is, whether or not it's a strong acid or strong base. You also have to be able to look at your titration curve and understand or figure out what your analyte is. And it could either be a strong base, a strong acid, or a weak acid and a weak base. So that's one thing you'll have to be able to do. Another thing that you'll have to be able to do is to determine the equivalence point. That means both the volume and the pH at the equivalence point, as well as the midpoint. Same thing for the midpoint. You will have to be able to figure out the volume and the pH at the midpoint. And we'll explain what all this stuff is as we go further into talking about these titration curves. Another thing that you'll have to be able to do using these titration curves is determine the Ka value of your analyte that you have present there. So we will be able to look at the graph and do a calculation to figure out the Ka value. Last but not least, number 4, and this is the main component that will help you for multiple choice questions. They can do like molecular, like particulate diagrams with these molecular ratios. They could ask you which section has more of something than the other. And also this will honestly help us with our big picture as well. So molecular ratios along the curve. And again, this is just things that you need to know how to do. Make sure you write that down so you can self-evaluate to figure out if you can do these or not. We are going to go through each of these components as we go further into the video. All right, so now that we have a clear understanding of what you have to be able to know how to do from a titration curve given to me, let's kind of go into this page and decipher what we need to do. So this is our titration setup that we have here. So again, burette contains, this one obviously contains the base, but it doesn't have to be the base. So the burette is containing the titrant. And that's usually a strong acid or a strong base there. The flask contains the analyte, which is the thing we're analyzing, and that could be a weak acid, weak base, strong acid, or strong base. All right, so we have to be able to use our titration curve to figure out which one that is. Also, just a review, we also need the indicator, the appropriate indicator in our flask in order to figure out what the equivalence point and the endpoint is, which they're the same as long as we have the correct indicator. So what I want to do is look over to the right at these two titration curves, okay? So first of all of your titration curves are going to have pH on your y-axis and volume of your titrant. So volume of your titrant, whatever is in your burette, that is on your x-axis. Now, sometimes they don't say specifically what your titrant is here, so they might just say volume added or something like that. So we have to be able to use this curve in order to figure out, first of all, the components involved. So what I do is I look at the initial pH, so the very beginning of the pH at volume 0. And if I look at that pH, I can determine what the analyte is. So your beginning pH is going to tell you what your analyte is, whether or not it's a strong acid, strong base, weak acid, or weak base. So we got to kind of decipher a couple of things before we get into this. First of all, if I have a strong acid, what will my pH range basically be? Well, strong acids have a pH of around 1 to 2. Weak acids have a pH range basically around 3 to 5-ish, okay? Strong bases have a pH of around 13 to 14, and weak bases have a pH range of about 8 to 11-ish. All right, so what I can do is I look at the very beginning pH, and that tells me what my analyte is. Because this beginning pH is around 1, that tells me that my analyte for this, oh, my bad. Hold on, let me erase this. My analyte for my titration, so what's in my flask, is going to be a strong acid. The next thing that I do is look at my ending pH. Where my ending pH is, that is going to tell me what my titrant is. So my analyte is the strong acid. I look at the beginning pH. The ending pH is somewhere around 13. So what that tells me is that my titrant is a strong base. So if I were to look over here at my experiment, what would be in the burette would be a strong base, and what would be in my flask would be a strong acid. So this is a strong base, strong acid titration. If I look at this one here, all right, my beginning pH is around 13. So that means that my analyte is going to be a strong base. My ending pH is around 1, so that means that my titrant is a strong acid. So this is also a strong acid, strong base titration, but my strong base is what's present in my flask, and my strong acid is what's present in my burette. Okay. Equivalence point. How do we figure out the equivalence point? Well, you see that all titration curves have a general portion in which it doesn't really increase much, and then it spikes, whether it's up spike or down spike, and then it kind of levels off again. Okay, so you see this one is just opposite of this one. Okay, when I have a strong acid, strong base, my equivalence point is always going to be a pH of 7. So strong acid, strong base, as long as both of them are your analyte and titrant, then my pH at the equivalence point is going to be 7. pH here, equivalence point 7. Where my volume at the equivalence point is going to be dependent upon what molarities that you're actually using for this analyte and titrant. Okay, but your pH at the equivalence point for strong acid, strong base titrations will always be 7. Okay, how I can figure out my equivalence point is it's always this region of where you have the spike. Okay, so you see gradual, spike, gradual, gradual, spike, gradual. So if I look at the spike and I figure out the halfway point, right, the middle portion of that spike, that is where my equivalence point is at. Now, and remember, equivalence point means that's when all of the acid or all of the base, whatever the analyte is, has been neutralized by the opposite. Okay, so that's how I figure out my equivalence point. My midpoint is located at half the volume of my equivalence point. So you see how my equivalence point volume here is 25. Sorry, I have people over. Hush, but hold on. Let me get them to chill out. Sorry, I swear one of these days I'm going to make a video in which there's no interruptions. So, equivalence point P is 7. Where I figure out my equivalence point is where it spikes, and it's the middle of that spike is where my equivalence point lies. Now, again, that's when all of the substance has been neutralized by the opposite. So, all of the analyte essentially has been neutralized by the titrant. That's what is happening there. Okay, so let me see what we've taken care of here. All right, determine the Ka and molecular ratios. I want to go to another thing here. Let's look at these two. All right, so first, let's take care of all of the answers that we've had, or all of the components that we need to know. So for step 1, we want to figure out what is the analyte, and we want to know what is the titrant. So again, for our analyte, we look at the beginning pH, and you see that this beginning pH is around 3. So what that tells me is that the analyte is a weak acid, because weak acids have pHs around 3 to 5. Then we look at my titrant. All right, my titrant is the ending pH here. So this pH is around 13. So what that tells me is that there is a strong base that is my titrant. So I have identified the components that are involved. Step 2 is we want to figure out the equivalence point pH and the equivalence point volume. So equivalence point pH and volume. The equivalence point pH, remember I look at the spike, and I would say halfway in between that spike is probably somewhere right here. So I would say my equivalence point pH is somewhere around 9. My equivalence point volume is I look at where that spike is on the x-axis. It's the volume of NaOH added. So that would be 25 milliliters. Step 3 is, I'm sorry, we need to do the midpoint too, don't we? So let's do the midpoint first. So midpoint, the midpoint pH. So what I do to find the midpoint is I look at my volume at the equivalence point and I take half of that volume. So half of that volume would probably be somewhere around here. 12.5 is half of 25. So this would be my midpoint. So my midpoint pH is somewhere between 4 and 5. I'm just going to say that it's around 5. And my midpoint volume is going to be 12.5 milliliters. So that's what equivalence point, midpoint, how we find that. Step 3, we want to figure out the Ka. All right, so let's talk about how to figure out the Ka. Well, if I take my pH at the midpoint, my pH at the midpoint is equal to the pKa of my acid. And if you've watched my other video about the indicators, pKa just means negative log of Ka. So what I'm going to have to do here is plug in the pH at midpoint, and then I can solve for the Ka. So my pH at midpoint, I said, was 5, right? So 5 is equal to pKa, which is negative log of Ka. And so in order to get Ka by itself, remember log is 10 based, so it's 10. I take this negative and this answer here and I fishhook it. So 10 to the negative 5 is equal to Ka. Now this is not a correct answer. I have to put it in correct scientific notation. So this would translate to 1 times 10 to the negative 5th is equal to my Ka. And what is that the Ka of? It's the Ka of the weak acid that I'm starting with there. So that's how I find the Ka value. I have to look at my midpoint, only my midpoint, and then I solve for my Ka like that. Now, the next thing is molecular ratios. How do I figure out molecular ratios along the curve? Okay, well, in order to do that, I have to kind of figure out what my reaction would be. So I'm going to write the net ionic equation for this particular thing. So it'll be HA plus OH minus yields H2O plus A minus. So this would be the net ionic equation for the reaction we see here on the left. Okay. So what exactly is happening as I'm going through the titration? Well, at the very beginning, at time 0, all right, all that I have present there is weak acid, all right? So all that I have present at time 0, so at volume equals 0, all that is present is my weak acid. So that is the only species that I have present there. But once I put one single drop of the titrant in here, notice how your pH is not really changing that drastically, right? Well, this is something new I have to introduce, but we're going to really get deep into it. This region that you see before the spike, before the equivalence point, because the pH is not changing, it is known as a buffer region. Very important to know. Buffer region. So we've got to understand what a buffer is. I'm just going to give you this is what you need to know for now until we get deep into it. A buffer resists a change in pH. Okay, so basically a buffer keeps the pH from changing. And we see that, right? Because our pH is not changing very much, right? Until we get to the spike here. So that is why we have a buffer region here. More specifically, when you have a buffer, you have to have two specific components there. You have to have a weak acid with its conjugate base, and we all know about weak acid conjugate base pairs, or a weak base with its conjugate acid pair. So we should know, based upon our acid-base introduction kind of video, how to figure out a weak acid and its conjugate base, or a weak base and its conjugate acid. You have to have both components there in order to have a buffer. And we will definitely get into that. You will fully understand that when we talk about buffers. But this is just important to introduce these titration curves, some information you need to know now. So we have our buffer region. So what we have here, all right, before the midpoint, so this is at the beginning, before the midpoint, what we have present there is HA, definitely, but when this is starting to react, we're also getting some A minus, okay? So HA, remember, is our acid. A minus is our conjugate base, weak acid to be specific. So remember when I said what a buffer was? It was weak acid and conjugate base. Well, guess what? We have a buffer there. So both of these species are present throughout this whole entire buffer region. Okay, so both the weak acid and the conjugate base are present in the buffer region. We just need to know which is there more of. Okay, before the midpoint, you have more weak acid than conjugate base. So before weak acid, before the midpoint, your weak acid concentration is greater than your conjugate base concentration. At midpoint, because you're starting to make more and more of that conjugate base, right? You're making more and more of that conjugate base. At midpoint, your weak acid concentration is equal to your conjugate base concentration. And we will talk about that more specifically when we get to buffers, what that means. Okay? So before midpoint, weak acid is greater than conjugate base. At midpoint, weak acid is equal to conjugate base. So what do you think is happening after the midpoint? Well, after the midpoint, your weak acid, remember it's getting neutralized, it's going away, going away, going away. You now have more conjugate base than your weak acid. Okay? So that is what's happening along here. Before the midpoint is right in this area. At the midpoint is specifically at that volume 12.5. And after the midpoint is any time after you've reached the midpoint right there. So all of this is happening before you reach this equivalence point. Okay? Now, your next component is at the equivalence point. Well, what is happening at your equivalence point? Remember how I said that all of this HA has been neutralized? So basically, your reaction is gone for all of this to be gone. And guess what I have here now? I have just my conjugate base present. So at equivalence point, I have conjugate base only. I no longer have any weak acid. So you see how I have weak acid to start with. It's starting to decrease, but it's greater than conjugate base, starting to decrease more to where now they're equal. I'm starting to make more of this stuff, right? Decreasing this value, increasing that value if we were looking at a rice chart. And then now I have more and more conjugate base. Well, boom. I have totally neutralized my weak acid. So all that I have present there now is my conjugate base. Now, one more thing. You see how at the, let me scroll back up so you can see. You see how after the equivalence point, you're kind of leveling off again here, right? Well, the reason why that is happening, no, you do not have a buffer there. Okay, that is not a buffer region. What's happening is you have just conjugate base there, but you're adding more of the strong base, right? Well, a conjugate base and a strong base doesn't really react with one another, right? It's always an acid and a base. The opposites have to react with one another. So because I have conjugate base there, but I'm also still adding more strong base, you just have some OHs floating around and the conjugate base floating around. So after the equivalence point, what do I have present there? Well, I have conjugate base there, and I also just have some OHs that are floating around in my solution as well. So that's why my pH is pretty high, but it's not really changing drastically. Why is that? Because pH is 10 based. I have to change my concentration by 10 in order to get my pH to change. So because I'm just maybe increasing OH a little bit, but I'm not increasing it by a factor of 10, my pH is not changing from there. Okay, so this is what we're talking about when we say molecular ratios. You need to know what's happening there. So let's take this idea and let's apply it to the next titration curve, which is right here. So I think I'm going to choose a different color like green maybe to figure out what's happening. All right, so first, what is my analyte? My analyte is starting at a pH of 11, so that means I have a weak base. That is my analyte. What is my titrant? My titrant is around a pH of 1, so that means my titrant is a strong acid. Where is my equivalence point? Well, it's here at the spike in the middle. What is the pH at my equivalence point? It looks to me like it's around 5. What is my volume at equivalence point? That one's between 20 and 25. I'm just going to make my best guess and call that 22 milliliters. So therefore, what would my midpoint be? My midpoint would be at a volume of 11 milliliters. And so 11 seems like it would be somewhere right here. So that would be my midpoint right there. That pH seems to be around 9. How do I find the Ka value of my analyte? Well, what I'm going to do is I'm going to say pH at midpoint, so 9, is equal to negative log of Ka. And so 1 times 10 to the negative 9 is equal to my Ka value. Now, this is a weak base, right? So weak bases, we usually have Kb values. But what I have of this base is a Ka value. So what if they wanted a Kb value? Well, if you remember, Ka times Kb is equal to that Kw for water, which is 1 times 10 to the negative 14. So if they want a Kb instead of a Ka, because our analyte is a weak base, all you have to do is find your Ka value, plug it into this equation by dividing 1 times 10 to the negative 14 divided by Ka, which in this case would be 1 times 10 to the negative 9, and that will give me my Kb value. So that's how you do it if they want Kb, because we're working with a weak base here instead of a weak acid on the left. For the next one, what are our molecular ratios? So I'm going to write it here on the graph. So at the very beginning, I have weak base only. Before the midpoint, I have weak base, but it's greater than my conjugate acid. You see how this is different from this reaction here, right? I have, let's see if we can write the reaction here. I have my weak base, so it's like BOH plus H plus, because my acid's my titrant, right? And what's happening here is this base is getting the H plus. So I have, let's see, H2O that's being produced. And then this base is actually getting an H plus as well. All right. So this BOH is going to be, or H2O, hold on. I got to backtrack here. Just 1 second. All right, let me show you with an actual reaction here. So what I have is NH3, which is a weak base. And this is what we're going to be dealing with mainly. So that's why I'm showing this to you. An H plus. So the H plus is coming from the strong acid here. So my base is getting the H plus, right? So getting the H plus, and that's forming my acid, my conjugate acid that is present here. So what I have here is my weak base, and I have my conjugate acid that's present there. And that's kind of what we were seeing from the other reaction that I wrote, but I can tell that it was a little bit confusing. So weak base, conjugate acid is what I have. So I'm starting out with more weak base. I'm making more conjugate acid as this H plus is going and reacting and reacting and reacting. Well, at the midpoint, weak base is equal to the conjugate acid. After the midpoint, weak base is less than the conjugate acid. At the equivalence point, I just have my conjugate acid only, right? Because all of that has been neutralized. And then after the equivalence point, I have conjugate acid, but I also have H pluses that are floating around in the solution because I keep adding more and it has nothing to react with. So being able to pick apart the molecular ratios for both a weak acid strong base titration as well as a weak base strong acid titration is really important. So that's kind of how we look at all of these things here. I want to show you one more thing before we're done with this video. So let me get a second to scroll down to there. So I want to scroll to another page. Let me see if I can find it. Here we go. So let's look at this one here, okay? So what is actually happening in this? It doesn't look like the general form that we've seen, like this one here, right? So what is actually happening? Well, this is a representation of what we call a diprotic acid. Diprotic meaning that I have more than one hydrogen, specifically di meaning two. So there's two H pluses that I'm giving off. Now, if you remember from the introduction to acid base, I have two hydrogens that I can actually donate, but I'm only going to donate one hydrogen at a time. So, what is actually happening here? So, I have a weak acid and a strong base. And weak acid is my analyte, strong base is my titrant. And you see how you have a buffer region here, and then you have your spike. So you have your first equivalence point. Now, at your first equivalence point, that is when you have given off one proton. So your acid here is H2A, the conjugate base is HA minus. So same ordeal that we've seen with a weak acid, strong base, that's what's happening in this region. But you can keep on going because there's another H that the reaction can actually, or that the acid can actually get. So now I have HA, I add more base, and boom, I reach a second equivalence point. At the second equivalence point, is when the second H plus has been given to the base, and therefore you have created another conjugate base, which is A2 minus. So we actually have two equivalence points that are here. And the two equivalence points lets us know that we have a diprotic acid. You can have three. If we had a triprotic acid, or polyprotic, then you would actually see three equivalence points that are there. So what are the percentages of actually things that are happening here? Well, as you're actually giving off each H plus, it gets to be a smaller and smaller Ka value. So what we have here is we have 100% at the very beginning of H2A. Well, now we have H2A, which is greater than HA minus. We have 50-50 H2A and HA minus. Remember, that's weak acid, conjugate base. Weak acid, which is greater than conjugate base. At the equivalence point, you have 100% conjugate base. These should say HA minus on here. And then we have another buffer region, right? We have HA minus, which is greater than A2 minus. We have A, which is equal, HA minus, which is equal A2 minus. And past the midpoint, we have HA minus, which is less than A2 minus. And then at this equivalence point, we have all of this conjugate base present there, which is A2 minus. So you're seeing the molecular ratios as you go along. So mainly when you're working with these diprotic or everything titration curves, you're trying to figure out what species is present at particular points, or you're just trying to figure out how many hydrogens it actually has to give. So it doesn't ask questions very often about this, but you should be able to understand those when they are asked. So I believe that is it for titration curves. Later on, we'll talk about what we need to figure out in order to sketch our own titration curve. We'll talk about that whenever we are working on our lab. So I hope this is helpful, and I will see you later.